The most common types of carbon nucleophiles that we use to add to aldehydes or ketones are organometallics. And just like the name implies, this is when we use metals and combine them with organic compounds. And so organometallics are, of course, organic compounds that include metals. We're going to talk about two main flavors of organometallics. We're going to talk about organolithiums. So we're going to talk about lithium, and we're going to talk about magnesium today. Right, and so the main thing to notice about lithium and magnesium is if we look at a periodic table, which I'm going to briefly sketch. If we were in a classroom, I would just kind of gesture to the periodic table that's on the wall, but since we're not, I have to try and draw one. So lithium, of course, is element 3, so it's right here under hydrogen. And magnesium is element something, like 12 or something like that. So it's over here. But both are on this far left side of the periodic table compared to, of course, carbon, which is over here. So electronegativity-wise, these are going to be much less electronegative than carbon. And so if we make a carbon-lithium bond or a carbon-magnesium bond, if we look at the polarity of these bonds, the electrons are going to be attracted to the more electronegative atom, which means we're going to get dipoles on these bonds. These bonds will be polar, but they'll be polarized in the direction of the carbon. And so the carbon will have a pretty significant delta minus, while the metals, lithium or magnesium, will have a pretty significant delta plus. Now, of course, this matches up pretty nicely with the carbon nucleophiles that we saw in the previous video, right? The carbon nucleophiles here, we had full-blown formal minus charges. We had a minus charge on the cyanide, we had a minus charge on the conjugate base of our terminal alkyne. Right? So when we have a full-blown negative charge, formal charge, they are very good nucleophiles. When we attach the carbon to a metal, kind of the same thing happens. The result of this polarity is nucleophilic carbon. Right? The carbon essentially reacts as a negatively charged carbon. Okay? And so if we can make these carbon-lithium bonds or carbon-magnesium bonds, you can imagine what's going to happen when we react these organometallic compounds with whatever carbonyl we have, right? So aldehydes or ketones. So let's say that let's take one bromobutane. So one bromobutane. You take one bromobutane, you react it with 2 equivalents of lithium metal. Right, so lithium 0 is just elemental lithium, so it's lithium in the 0 oxidation state. It has no charge, right? Metallic oxidation state, no charge. So that means that it has 1 valence electron, etc., etc., etc. Right. Okay, so what happens is that you're going to get 2 things out of this reaction. You're going to get the lithium will replace the bromine in that case, and you'll also get lithium bromide. Okay, so quick story time from graduate school. When you're in graduate school, other professors come and talk and give their talks at your school, and then they have all the graduate students sit and meet with the visiting professor and talk about, like, well, what is chemistry and how did you get into chemistry, whatever they want to talk about, whatever the graduate students want to talk about. So one of the guys came in and he was telling a story of a graduate student who basically got fired because he didn't know that you need 2 equivalents of lithium to convert an alkyl bromide into an alkyl lithium. Right? And so apparently this guy came in and one of the first reactions he ran in the lab was trying to convert this whatever bromobutane or something like that into the lithium reagent. and it didn't work, and it didn't work, and it didn't work. And so he went to his boss and said, I can't get this reaction to work. And they looked at his notebook and stuff, and they said, well, you only added one equivalent of lithium. He's like, well, what do you mean? He's like, well, you don't know why that's wrong. And apparently he got fired on the spot. Now, this is somebody who already had a PhD in whatever, and this is one of those stories that was a story of a story of a story, so who knows? But either way, I think I can safely say that by teaching you this reaction, I have most likely just saved your job in the future. So do one good deed every day. This is my good deed for today. Right? You need two equivalents of lithium because you need one equivalent to replace the bromine and the other one to make the lithium bromide. So you end up with two lithiums in your final product. But this is the thing that we're mostly interested in, right? This is the project. This is the product that we're actually going to use, right? So we've made an organolithium reagent, right? So what do we do with now butyl lithium? Butyl lithium is a very good base, right? So remember that this is negatively charged carbon. And so if we compare that, if we react this with any kind of acid, or even something that's not an acid, right, you're going to get a CH bond that's going to be neutral. And so this is going to be a very, very stable conjugate base, or conjugate acid, excuse me. Very stable conjugate acid. So if you have a stable conjugate acid, that means you have a very strong base. So butyl lithium is a very strong base, but it's also a good nucleophile. Right? So if we take this butyl lithium and we react it with some ketone or aldehyde, let's do a ketone. Let's use acetophenone. Right? Remember that this is basically carbon minus. And so that negative charge is going to attract it to the carbonyl carbon, because that's has a delta plus here, right? Delta minus there. And then that's going to push the electrons up onto the oxygen and make a lone pair there. And what you're going to get is you're going to get right? These four carbons are the four carbons that were a part of the butyl lithium, and then you're going to get lithium plus up here. So basically, we're going to take the electrons from this bond. They're going to go with the carbon and come in and attack here. The lithium will become a positive charge, and then that will just associate with this. You treat it with acid, H plus, and you would get a tertiary alcohol as your final product. So just like we did with the terminal alkyne, just like we did with the cyanide, what we're doing is we're adding a carbon to the carbonyl carbon, and we're adding some carbons, adding a chain to our thing. What we can do here is we can do this without a triple bond, right? We can do this with just single bonds. Because we can convert any alkyl halide using two equivalents of lithium into an organolithium reagent, which is pretty cool. Which is a nice thing, right? Adding carbons to things is the way that we do synthesis, the way that we make larger organic molecules. The problem is that organolithiums are hard to work with. They react with water really quickly. They can be potentially pyrophoric, meaning they can start on fire when they come in contact with air, which is not the most fun thing to be working with in the lab. Right. And so usually, unless you need to, we don't really pull butyl lithium out of the refrigerator unless that's the only thing that will work. So there's got to be a better way. And in fact, there is. The better way is magnesium. So let's take bromobutane, and now we're going to treat this with one equivalent of magnesium. So you won't have to lose your job over this one. And the magnesium just inserts itself between the carbon and the bromine. And this is because metallic magnesium has two valence electrons, so it can make two bonds. Basically, it makes a bond to the carbon, it makes a bond to the bromine. But functionally, this is exactly the same thing as we had before. We have a delta minus here, we have a delta plus over here. And so when this is an organomagnesium reagent, although they have a different name, they're named after the guy who kind of discovered their use. So this is called a Grignard reagent. And if you take a Grignard reagent and react it with a ketone or an aldehyde, let's do an aldehyde this time. We'll do, I think I used this one in the problem set, so I got to change this up a little bit. We'll do this one here. Okay. Remember, we're going to use the electrons from this carbon-magnesium bond. That means that the negatively charged carbon is going to end up attacking the carbonyl carbon. We're going to break the carbon-oxygen pi bond. We're going to push those electrons to the oxygen and make a lone pair there. And we're going to get O minus, magnesium plus, and our hydrogen is still there, but now we've got, we added 4 carbons, 1, 2, 3, 4. Okay. So all of this stuff gets added on. This is from the Grignard reagent. Everything else in here is from the original aldehyde. So again, we have to be sure that we're adding all our carbons. We have 1, 2, 3, 4 carbons in our Grignard reagent. We need to have 4 carbons added on here. And then of course we would treat this with acid. Where's my, I lost my pen. There it is. H plus. Right, treat this with a little bit of acid and now you get yourself a secondary alcohol. So we've gone from a 5-carbon aldehyde to now a 9-carbon secondary alcohol. This is one of the really common ways that organic chemists use to add more carbons to their structures, right? We use an organometallic, we add it to a carbonyl, and we convert that aldehyde or ketone into an alcohol. Right? There's no new mechanism here, really, right? We're not ever gonna ask you the mechanism for converting a halide into an organometallic. Just know that the halide gets replaced by the metal, right? So you get alkylithium or you get a Grignard reagent. Once you do that, then you add them to an aldehyde or ketone, and they do the same thing that all our other nucleophiles do. They add to the carbon, they break the pi bond, they push the electrons up onto the oxygen, and away we go. So there will be some applications of this. We're going to use organometallics for a couple of different reactions as we go. This is by far the simplest one, so it's good to start simple, and we'll make it more complicated in the future. So look forward to that.